At small scale, an LLM call can feel simple. In production, every token, retry, cache miss, and queued request starts to matter. In this lesson, we'll focus on the practical levers that keep GenAI systems fast, affordable, reliable, and safe. We've now moved from foundations to operations to optimization. Earlier modules covered production architectures, RAG, deployment, observability, security, and governance. Topics 5.1 and 5.2 introduced cost drivers and routing choices. Now we'll focus on runtime techniques that reduce latency and spend without sacrificing quality. Production optimization is a balancing act, not a race toward one metric. Faster responses may come from caching, shorter prompts, or smaller models, but each option can affect quality or safety. Lower cost comes from reducing unnecessary tokens, retrieval calls, embedding calls, and model invocations, while preserving the context the answer depends on. Reliability adds another layer. Quotas, retries, outages, and traffic bursts all need graceful handling. The goal is not maximum speed or minimum spend. It is the best acceptable balance for the user, the business, and the risk profile. Caching in LLM systems is not a single technique. It is a set of reuse points along the request path. Exact match caching works when the same normalized input should produce the same answer. Semantic caching is broader. When two questions mean the same thing, you may be able to reuse or adapt a previous result. Retrieval and embedding caches reduce repeated vector searches, document loading, and embedding calls. Prompt prefix caching can reuse shared instructions, schemas, and long static context when the provider supports it. The main design choice is matching each cache to the stability of that layer, then setting careful invalidation rules. Two caching patterns often deliver quick latency wins. Exact match caching is useful for repeatable requests, such as FAQs, policy lookups, classifications, or templated responses. If the normalized cache key matches, the stored answer can return immediately. Prefix caching works differently. It reuses expensive shared context, such as system instructions, tool specs, schemas, or background documents, while still processing the user's unique question. The discipline is safety. Never cache only by user text. Include model versions, parameters, tenant, locale, authorization scope, TTLs, metrics, and bypass rules. Semantic caching extends reuse beyond identical wording. The system embeds a new request, compares it with previously answered requests, and reuses an answer when the meaning is close enough. The similarity threshold is the key control. Too loose, and the cache may return a confident but wrong response. Too strict, and most of the savings disappear. For safer reuse, store more than the answer. Sources, prompt and model versions, freshness, safety labels, and evaluation scores. Then validate tenant access, authorization, and freshness before serving the cached response. In a RAG system, much of the expensive work happens before the model generates anything. Cache embeddings for repeated queries, document chunks, and summaries to avoid recomputing vectors. Cache retrieval results as well. Top matches, scores, filters, re-ranker outputs, and the final context window. Source documents, metadata, transformed formats, and access control decisions may also be worth caching, because assembling context can be surprisingly costly. The key requirement is versioning. A cache hit is only safe when the corpus, chunking method, embedding model, vector index, and ACL policy match the current request. Caching is also a production control concern. Every cached answer is something that can expire, leak, or cross an authorization boundary. Invalidate entries when prompts, models, documents, indexes, tools, policies, or guardrails change. Be especially cautious with personal data, regulated data, secrets, and tenant-specific outputs. The cache key must reflect who is asking, what they are allowed to see, and which policy applies. Finally, measure caching quality. Hit rate, stale hits, safety failures, user feedback, and evaluation regressions. Cache invalidation belongs in release management. Batching separates urgency from workload. When a user is waiting, keep the interactive path fast, then move non-essential work into a queue or scheduled job. This is effective for summarization, embeddings, evaluations, enrichment, classification, extraction, and back-office automation. Batch processing can improve throughput and reduce cost because it lowers request overhead and can use delayed execution. reliability still matters. Each batch task should be idempotent, so retries are safe, duplicates are ignored, partial failures are recoverable, and progress can resume from checkpoints. A queue-based design separates accepting work from performing the expensive model call. The API validates the request, applies rate limits, and places a job into a durable queue. Workers pull jobs when capacity is available, call the model, and write outputs to a result store. If something fails, retries use counters, visibility timeouts, and idempotency keys, so the same job is not processed incorrectly. Bad messages move to a dead letter queue for review. Users can receive progress updates, callbacks, emails, or webhooks, making this pattern useful for bulk summaries, reports, document processing, and labeling. Rate limits are operating constraints, not just errors to handle afterwards. Start by understanding every quota dimension: requests, tokens, concurrency, batch sizes, context windows, and region-specific limits. Then shape demand before it reaches the model provider. Give tenants and users fair budgets, classify priority, and cap oversized requests. When capacity tightens, admission control decides whether to reject, defer, queue, or downgrade to a cheaper path. Make quota visible with headers, dashboards, 429s, token burn, and remaining capacity so the system slows gracefully instead of failing suddenly. Resilient GenAI systems handle overload before it becomes an outage. Capacity signals should move upstream through queue depth, rate limits, degraded modes, or temporary rejection, so callers know to slow down. When requests fail, retries need exponential backoff, jitter, retry budgets, and idempotency keys, especially for 429s, 500s, and timeouts. Concurrency limits prevent one model, provider, or worker pool from being flooded. Failover can route traffic to another provider or smaller model, but only after checking prompt compatibility, quality, safety policy, and cost. Every path should record the outcome. Often, the fastest optimization is not a new model. It is sending fewer tokens. Tighten the prompt by removing repeated rules, shortening examples, and turning long guidance into clear directives. Prune retrieved context by keeping only the most relevant chunks, capping top K, deduplicating overlap, and stripping metadata the model will not use. For conversations, replace full history with a compact running summary. Constrain the answer with max tokens, a defined format, and a request for concise responses. Measure tokens before and after every change. Optimization is a control loop, not a one-time cleanup. Make outputs more predictable with schemas, function calls, constrained decoding, or typed responses, reducing parsing failures and wasted tokens. Measure the full request path: P50 and P95 latency, token use, cache hits, queue time, retries, cost, and quality. Before changing production behavior, test variants with shadow traffic, A/B experiments, and golden datasets. Then tune from evidence: context size, cache thresholds, batching, concurrency, routing, and prompts. The aim is improvement without hidden quality or safety regressions. Before scaling GenAI, optimize the work itself. Cache safely where reuse is likely. Batch tasks that do not need instant responses. Shape traffic with queues, retries, backpressure, and provider failover. Reduce unnecessary context and tokens. These habits improve speed, cost, and reliability, and they set up the next step: auto-scaling, capacity planning, and FinOps.